Math 2414, trigonometric integrals, integrating a product of sines and or cosines, part 3. At the end of the last video, well during the last video, we kind of built this technique that says if you're integrating a product of sines and cosines, and one of the powers is odd, you let u equal the other trig function, and when the time is right, you use a Pythagorean identity to replace the unwanted trig functions. But what happens if both of the powers are odd? The answer is you can't go wrong, because the whole premise is to let u equal one trig function and then borrow one from the other for the du package, leaving those even and using a Pythagorean identity. So technically on this one, I could treat the sine as the odd power and let u equal cosine, or I could treat cosine as the odd power and let u equal sine. So they both will work. But is one better than the other? And the answer is absolutely. If you recall from the previous video, we had a cosine to the fourth power that we had to rewrite as cosine squared x squared because the cosines were unwanted, and then we replaced cosine squared with 1 minus sine squared, and then u is equal to sine, so we had 1 minus u squared squared. So we had that in our integral, but when it came time to integrate it, we had to FOIL this out. Because the power was big and it left some power over here, if this were a 6, heaven help us, this would be a cube. And although it's not impossible to write 1 minus u squared 3 times and multiply it all out, it just starts becoming tedious and cumbersome. So where am I going with that train of thought? That train of thought is, for your unwanted trig functions, whichever one's not the substitution, for your unwanted trig functions, smaller powers are better. So how do we turn that into a strategy? Well, by saying the following. Here's my red marker. You're wondering why I never use these markers. They just really serve as boundaries for the video. There are black lines under there, but when I erase, they tend to get erased. But these markers help me preserve those boundaries. So let's, this is a continuation of this technique. If both powers are odd, comma, let u equal the trig function with the higher power. Let u equal the trig function with the higher power, semicolon, borrow from the lower power, or from the lesser power. I know I'm being persnickety with my adjectives, but I really should say greater and lesser, because when you compare numbers, it's greater than and less than. If both powers are odd, let u equal the trig function with a greater power, borrow from the lesser power for the du package. That will leave fewer unwanted trig functions and make the last substitution easier. Really all you have to do on these is make the correct decision for letting u equal. So if you want to boil it down, if one of the powers is odd, let u equal the other power. And if you have a choice, let it be the trig function with the higher of the two powers. All right, so using that guideline, we're going to let u equal cosine x. Both powers are odd, so either substitution will work. So we're going to let u be the trig function with the higher power. Let u equal cosine x. Then du is equal to negative sine x dx. So let's see what we have to do to get this going. All right, let's start by thinking about the du package, which needs a sine. So we're going to steal one from here. That'll leave a sine squared x. Our cosine is going to stay there. We didn't borrow from it. We are borrowing one of our 3 sines to put with the dx, because we need to start building this du package, which needs a dx always. Needs a sine x, which we have one, but it's missing a negative. That's easy. Throw a negative in, balance it on the outside. And now that negative, along with the sine x and dx, to complete the du package. Of the remaining trig functions, who's unwanted? Well, who's our substitution? Our substitution is cosine, so cosine to the fifth becomes u to the fifth. But these guys, the sine squared x, this is what I'm referring to as unwanted. I wanted cosines. Cosines become u's. I don't want sines. So now we use Pythagorean identity to rewrite sine squared. Well, that's easy. Sine squared is 1 minus cosine squared. This becomes 1 minus cosine squared x. But in terms of the substitution, that will become 1 minus u squared, since u is cosine. And so now our integral is negative, don't forget that, integral 1 minus u squared, u to the 5th du. This will be pretty easy to deal with. We'll deal with the negative after we integrate. Let's distribute the u to the 5th because we don't integrate products. We integrate sums and differences. Integral of u to the 5th minus u to the 7th du. And at this point, we're going to integrate, change the u's back to cosines, and distribute the negative all in one fell swoop. By the way, if that sounds like too much for you, don't do it all at once. But little algebra moves, and I do consider those little algebra moves, distributing the negative, rearranging the terms from highest to lowest power. I don't mind if you multitask those. Just be careful, and if you can't, then don't. Do them one step at a time. All right, so let's integrate this, put it in the right order, and change the u's. The integral of u to the 7th is 1/8 u to the 8th, but it will become positive. So 1/8 u to the 8th, but u is cosine, minus the integral of u to the 5th is 1/6 u to the 6th, but u is cosine of x. So we have 1 minus 1/6 cosine of the 6x plus c, and the integral is over. It would have worked had we said u equals sine of x, and I'm going to do that one just to show you how it would be different and similar. And in fact, if we had made a different substitution, our answer would have looked different. I do want to leave that answer somewhere. I'm going to squeeze it right under here. 1/8 cosine of the 8th x minus 1/6 cosine of the 6th x plus c. And by the way, if you're wondering how to take the derivative and then restore it back to that, take the derivative, watch your chain rule. This will knock down the cosine to the 5th. You can factor out a common factor of cosine to the 5th. There will be a Pythagorean identity, which will sneak some more signs in there. When it all washes out, you'll get back to the original integrand. But if both powers are odd, I would let u be the trig function with the higher power, because the other trig function will be your unwanted trig function, and it will be easier to use a Pythagorean identity to change it when the time is right. But what would have happened if we just said, we'll let u equal sine x? It won't be wrong, and we'll get another answer, but it will be a little more challenging to get there. Watch what happens. If we said let u equal sine x, then du equals cosine x dx. It's going to be real easy to build the du package. We just need to borrow one of the cosines and put it with the dx. So the sines will stay put, and that will leave me 4 cosines. Oh, wait a minute, we've already told this story. The du package is already created. Cosine x dx, all that becomes du. We want sines, they become u's, so sine cubed becomes u cubed. But we don't want cosines because that's not what u equals, that's our unwanted trig function. Well, we've already talked about how to take something like cosine to the 4th and turn it into sines. Just to recap, cosine of the 4th x is equal to cosine squared x squared, which is equal to 1 minus sine squared x squared, and then the sine becomes u for this substitution. So cosine to the 4th becomes the square of 1 minus u squared. So our integral is now the integral of u cubed times 1 minus u squared squared du. And again, from an algebra perspective, we don't integrate products, we integrate sums and differences. So we would have to bust this open. I'm not going to dilly-dally with the algebra. We've already squared this. We know what it equals. It's 1 minus 2u squared plus u to the 4th. If we distribute the u cubed, again, I'm bypassing a lot of the algebra. You would get u to the 7th minus 2u to the 5th plus u to the 3rd du. Double check that. Yes, yes, yes. I feel like Meg Ryan. most of you probably don't get that joke. Go watch When Harry Met Sally. And if we integrate this and change the u's back to sines, we get 1/8 sine to the 8th power of x minus 2/6, which reduces to 1/3 sine to the 6th power of x plus 1/4 sine to the 4th power of x plus c. And on the surface, these two answers look completely different. Well, not completely, they both have 8s and 6s for powers. This guy's got an extra term, but with a little bit of smoke and mirrors, you could take advantage of some identities and turn this into that. We're not going to do that. The point I'm trying to make in this video is, if you're integrating a product of sines and cosines, and both powers are odd, you should let u be the higher powered trig function. In this case, u equals cosine. If you don't, then you will have more algebra to dig your way out of. It's not wrong. I'm just trying to give you the path of least resistance. All right, so there's one more thing that we have to figure out before we move beyond sines and cosines, and that's what happens if none of the powers are odd, which means that both of the powers are even. We'll start off simple and then we'll raise the bar. I'm predicting 2 more videos for sines and cosines.